नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। दिस इज द 9th डे ऑफ JEE मेंस रिवीजन एंड today I am going to discuss about thermodynamic part 3. In this video I am going to discuss about Gibbs free energy in detail and about thermochemistry. यदि आप हमारे चैनल पे नए हैं और आपने हमारे चैनल को सब्सक्राइब नहीं किया है तो कृपया करके उसे सब्सक्राइब करिए। वीडियो देखने के बाद अगर आपको अच्छा लगता है तो उसे लाइक कीजिए। तो आइए शुरू करते हैं। पहले हम गिब्स फ्री एनर्जी के बारे में डिस्कस करेंगे, देन विल डिस्कस अबाउट थर्मोकेमिस्ट्री। सो मोस्ट ऑफ अस फील अनकंफर्टेबल रिगार्डिंग दिस गिब्स फ्री एनर्जी, सो आई एम गोइंग टू डिस्कस दोज थिंग्स व्हिच वी शुड नो, बट मोस्ट ऑफ द टाइम वी डोंट नो अबाउट दैट, सो वी फील लिटिल बिट कंफ्यूज्ड. So let us discuss one by one about this Gibbs free energy. So this is a reversible reaction. Small a capital A in gaseous state plus small b capital B in gaseous state will form the products, and it is a balanced reaction. All the reactants and products are in gaseous state. So when we write delta G of this reaction, what is the meaning of delta G of this reaction, that we want to understand. And we also want to understand that delta G reaction is equal to delta G naught reaction plus RT ln Q. How to derive that and what is the meaning of that, right? So the first thing we are starting here, the graph is mentioned here. So this is G naught reactant and G naught product, and the difference of these two is equal to delta G naught of the reaction. So when we are discussing that what is delta G naught of the reaction, delta G naught is equal to standard Gibbs free energy of product minus standard Gibbs free energy of reactant. So what is the meaning of standard Gibbs free energy of product and reactant? Here in this diagram we can see that this is related to G naught of the reaction. This is G naught R. G naught R means the reactant are present at 1 bar pressure, and they should be pure form, right? They are not mixed, they are not in the same container, they are separately present at 1 bar pressure. 1 bar is a standard condition, so A is in a standard state, means the pressure of A should be 1 bar, and the number of moles of capital A should be according to balance reaction. So pure A is there, its moles is equal to according to stoichiometric coefficient, and it is present at 1 bar. B is there, it is in pure form, its moles is B according to balance reaction, and it is at 1 bar. So this represents G naught of reactant. Same way, when we are discussing that what is G naught of product, G naught of product is again the product C and D should be in pure form, and their moles is equal to the stoichiometric coefficient of the balance reaction, and they are respectively at pressure 1 bar and 1 bar. So definitely here they are not present in the form of mixture, they are pure form. The difference of these two things is delta G naught reaction. So we are saying that the difference of G naught of product minus G naught of reactant is this is straight line, and that the slope of the straight line we can say, or the, because here extent of reaction is 0 to 1, so change in y upon change in x is equal to slope of the line. So that's represent the value of delta G naught of the reaction. Now in this graph is related, this curve is related to Gibbs free energy of the whole system. So initially when the extent of reaction is equal to 0, only reactant is there, so this is G of reactant. It is not in a standard, right? G of reactant. And here when the extent of reaction is equal to 1, this will be G of product. G of product. So what is the meaning of G of reactant and G of product? Here we can see that in this box, when this reaction will start, initially A and B is formed. A and B is present in the same container in stoichiometric mole ratio, and the sum of the partial pressure of A and B is equal to capital P. Capital P is the pressure and temperature at which this reaction is taking place. We know that this reaction is taking place at constant pressure and temperature. So initially, the partial pressure of A plus partial pressure of B is equal to P, and temperature of this is T. So A and B is in mixed form, and the number of moles of A is equal to stoichiometric coefficient, the number of moles of B is equal to stoichiometric coefficient, and the sum of partial pressure of A and B is equal to total pressure of the system. Same way when we are discussing that what is Gibbs free energy of product, this Gibbs free energy of product when the extent of reaction is equal to 1, we can write that C and D are present in mixed form in their stoichiometric ratio, C moles of capital C, D moles of capital D. Partial pressure of C plus D is equal to total pressure, which is P. So the reaction is taking place at constant pressure. When the reaction will continue, when the value of extent of reaction will some positive value, when it is going on, right? When the reaction will going on in the reaction mixture, A, B, C, D, all four will be there. So this is the real case where this graph is related. When the reaction is going on, all A, B, C, D is present in the same container. Number of moles of A, B, C, and D and partial pressure of A, B, C, D is given. The sum of partial pressure of all these four is equal to total pressure. So we can say that during the reaction, the pressure is constant, that is P, and the reaction is taking place at constant temperature. So this is Gibbs free energy of reaction. When we are saying that what is delta G of the reaction, so this delta G of the reaction at any point of time when this reaction will proceed in forward direction, the Gibbs free energy will change by a small quantity. So we can say that delta G reaction, when we are discussing here that delta G reaction is 0, this delta G reaction is variation of Gibbs free energy of the system with respect to the extent of reaction, that is the slope of tangent at particular point on this Gibbs free energy of the system graph. We are taking a point. On that point, if we draw the tangent, the slope of tangent is delta G reaction. So slope of tangent here is negative, means delta G reaction is negative, and we know that delta G reaction is negative means reaction is spontaneous in forward direction. We can also say that when we are increasing the extent of reaction, what is extent of reaction? Like in mole concept, we are saying that initial moles of this capital A is A naught. When the reaction will proceed, we'll write A into X, right? And initial moles here is for B is B naught. Then we'll write that B naught minus Bx, and here it will form Cx plus Dx. Here X is known as the extent of reaction. So here it is denoted by chi, and it is the extent of reaction. At equilibrium condition, which is minima on this curve, at equilibrium condition, if we draw the slope of tangent, the slope of tangent at this point is equal to 0. So we are saying that at equilibrium, delta G reaction is equal to 0. So delta G reaction is the variation of Gibbs free energy of system with extent of reaction at a particular instant. It represents the slope of tangent on Gibbs free energy of the system versus extent of reaction graph. So that is a thing which we should understand. Now here, since Gibbs free energy is a state variable, we want to calculate that what is the value of delta G. So this is the initial state, and we can say that when the reaction will take place, this is the initial state and this will be the final state when the reaction will complete, and this is the intermediate state when the reaction is going on. So in order to move from initial state to final state, we either will go by this path, we can say that this path is path 1, or we can move by a second path where we'll move from here to here, then we'll move from here to here, and then we'll come back to here. So we can say that this path is equal to second path. So in order to calculate the change in Gibbs free energy from initial to final state, if I have to calculate this, in order to calculate what I am doing, that I am calculating what is the change in Gibbs free energy of mixing one. When pure A and pure B will mix, so this is mixing of ideal gas, assuming ideal gas, this is mixing of ideal gas at constant temperature. Pressure is not constant because initially A and B both are at 1 bar and now it is at P bar pressure. So pressure is not constant, but temperature is constant by using change in entropy while mixing of two gases. For gas A, if I say what is entropy change is equal to NCV ln T2 upon T1 plus NR ln V2 upon V1, or CP ln T2 upon T1 plus NR ln P1 upon P2. So using that formula, temperature is constant. So the first term is equal to 0. The second term, we can calculate entropy change. And now when we are mixing, since temperature is not changing, there is no change in enthalpy, right? So here when we are mixing at constant temperature and pressure, before and after mixing, temperature is same. So enthalpy change of an ideal gas depends on temperature change. So there is no temperature change. So delta G mixing is equal to delta H mixing minus T delta S mixing. From there we can calculate what is delta G mixing for this step, right? When we are moving from here to here, then we have already know that what is the value of delta G naught reaction. It represents gives G naught of product minus G naught of reactant. So this is delta G naught. And this is again mixing. Pure C and pure D at constant temperature will mix to form CD mixture. So again, by using delta G is equal to delta H minus T delta S for mixing, since temperature is not changing, delta H mixing will be 0. We can calculate what is entropy change of mixing. Entropy change, since temperature is constant, first term is 0. So we can write that entropy change is equal to number of moles of C into R ln P initial upon P final, and in that way we can write. So in the next page we are going to calculate, we are going to derive the formula, the relation between delta G and delta G naught. So let us try to derive the formula. Again, this graph is here. So what we are saying that this is the initial state of the system and this is the final state of the system, and we are moving from initial to final state by this path directly. This is path 1. We can choose another path. This is path 2. So since Gibbs free energy is a state variable, the change in Gibbs free energy in path 1 and path 2 will be same. So try to calculate the value of delta G reaction, right? When the reaction is progressing, we are writing this is delta G of the reaction, which is equal to delta G of the reaction is equal to minus times of delta G mixing 1 plus delta G naught of the reaction plus delta G mixing 2. This is delta G mixing 2. So first we'll calculate what is the value of delta G mixing 1. Let us calculate the value of delta G mixing 1. So in delta G mixing 1, we have already discussed delta H mixing will be 0. And we are using the formula delta G mixing is delta H mixing minus T delta S mixing, temperature T and delta S mixing 1. Delta S mixing 1 is what? Delta X mixing of gas A plus delta S mixing of gas B. Delta S mixing of gas A, because the first term is 0, so we can write NAR ln. Initial pressure was 1 bar and final pressure is PA in the mixture. Same way for B, we can write NB into R ln initial pressure upon final pressure in the mixture. So this is change in Gibbs free energy on mixing from this pure form to this. Delta G naught we already know. So similarly, we can calculate the value of delta G mixing 2, which is equal to plus RT ln PC to the power small c, PD to the power small d. Why we are writing small c and small d? Because here in the balance reaction, Na is equal to small a, Nb is equal to small b. So if I simplify this, numerator will go, denominator will go in numerator and this will become plus, and here Na is A and Nb is B. So now I can write this as RT ln PA upon 1 to the power A, PB upon 1 to the power B. So in this way, we have calculated the value of delta G mixing 1, delta G mixing 2. And now we are putting in this equation. So on putting the value of delta G mixing 1 and 2 in this equation, we can write that delta G reaction is delta G naught reaction plus RT ln partial pressure of C to the power C, partial pressure of D to the power D upon partial pressure of A to the power A, partial pressure of B to the power B, which is known as reaction quotient. So at a particular instant, change in Gibbs free energy will depend on the reaction quotient of the system. So delta G reaction is equal to delta G naught reaction plus RT ln reaction quotient. So this is the derivation of this. Now at equilibrium, we know that equilibrium means the minima on this Gibbs free energy versus extent of reaction graph. This is equilibrium. So at equilibrium, we can say that delta G of the reaction is always 0 because Gibbs free energy of the system is minimum. There is another relation. We know that delta G at constant temperature and pressure of the system is minus T delta S total. So at equilibrium, the Gibbs free energy of the system is minimized. It is at minimum value. It is minimum. That's why its change is equal to 0. And the entropy of universe is maximum. It is maximum. That's why its change in value is equal to 0 at equilibrium. So delta G is equal to minus times of T delta S total. So these 2 points are also important. So when we are discussing at equilibrium, delta G reaction is always 0. but delta G naught reaction will depend the value of equilibrium constant, because in the reaction, in this equation, if I say that the value of delta G reaction is equal to 0 at equilibrium, means the value of reaction quotient is equal to equilibrium constant. From there I can write that delta G naught of the reaction is minus RT ln equilibrium constant. So this relation, depending upon the value of equilibrium constant, the value of delta G naught will depend. So the value of delta G naught may be negative when equilibrium constant is greater than 1. From here, if equilibrium constant is greater than 1, ln K equilibrium will be positive, RT is positive, so delta G is negative. So based on this equation, we can say that delta G naught is negative when equilibrium constant is greater than 1, delta G naught is positive when equilibrium constant is less than 1, and delta G naught is equal to 0 when equilibrium constant is equal to 1. So there is a question in JEE Advanced that when the value of delta G naught is equal to 0, it may be 0 at equilibrium provided the value of equilibrium constant is equal to 1. So it may or may not be equal to 0 at equilibrium, but delta G is always 0 at equilibrium. In order to explain this, I have taken one example. We are familiar with the graph of pressure versus temperature for water. So this is the graph. And we know what is normal boiling point of water. At normal boiling point of water, the pressure is equal to 1 atm and temperature is 373.15 Kelvin. And at standard boiling point of water, the pressure is 1 bar. And in our gaseous state NCERT, they have given that the temperature at 1 bar pressure for boiling is 99.6. So we have already studied that normal boiling temperature is always greater than standard boiling temperature. So we are discussing the process of boiling at different conditions. So the first condition is normal boiling point. So at normal boiling point, I want to write what is Kp naught. So Kp naught is partial pressure of H2 under the given condition divided by partial pressure of H2 under standard condition, right? So here we should know when we are deriving and we are writing here, this one is important, 1 and Pa, right? So when equilibrium will be there, this is Pa at equilibrium, Pb at equilibrium, but 1 bar is there in the numerator, right? So if we simplify, we should know that when we are writing something in this relation, when we are writing something in log, it should be a unitless quantity, and that unitless quantity will come when in place of Kp and Kc, we should write Kp naught and Kc naught. And basically, we should use Kp naught and Kc naught. For simplification, we are writing Kp and Kc because numerically Kc and Kc naught is same. And according to old convention, Kp naught and Kp was same. Now, since the standard pressure is changed, because of that, the problem is coming. Otherwise, we should know that in the bracket, the value of equilibrium constant should be unitless quantity. So when we are writing here, what is the equilibrium constant Kp naught for vaporization of water at 1 atm? So that is vapor pressure of water under the given condition where it is in equilibrium divided by standard vapor pressure. So that is equal to 1 bar. So 1 atm is 1.01325 bars. So equilibrium constant here is greater than 1. And because of that, we can say that at point A, delta G naught, since equilibrium constant is greater than 1, delta G naught will be negative. Same way, we can write for B point. For B point, at B point, we can see this is normal standard boiling temperature. Pressure is 1 bar. So Kp naught is equal to pressure at equilibrium is 1 bar divided by standard pressure. So Kp naught is 1. So delta G naught is 1. So at standard boiling point of water, delta G is equal to 0. Delta G naught is also equals to 0. And let us discuss point C. Here it is triple point where solid, liquid and gaseous form of the substance is in equilibrium. For boiling, vaporization, if I write what is Kp naught is vapor pressure of water at this given condition, that is 0.006 atm. Atm can be converted into bar by multiplying it by 1.01325. So this is bar, pressure in bar, divided by standard pressure, that is 1. So here Kp naught is less than 1. If Kp naught is less than 1, delta G naught of the reaction is positive. So this is a best example to explain that At equilibrium, delta G is always 0, but delta G naught may be positive, may be negative, may be 0, depending upon the value of equilibrium constant. There are many questions in JEE mains based on this formula, right? So when we are solving this formula, delta G naught is equal to minus 2.303 RT log Kp naught. If I want to calculate this Kp naught, I have to solve this value. So if you go through NCERT, they have mentioned the value, this value at room temperature in terms of joule, when we are putting the value of R is equal to 8.314 and temperature is 298.15. So this value is 5709. So this is given in NCERT, and these are very common. These calculations are very common in the questions coming in mains and advanced. So you should remember so that you can directly put this value to save your time. Variation of Gibbs free energy with temperature. So here when we are writing variation of Gibbs free energy with temperature, we know that if G is equal to H minus Ts, G is equal to H minus Ts, when temperature is constant, delta G, if the conditions are standard, then delta G naught. If it is not, then delta G is equal to delta H minus T delta S. So most of the data we got is in a standard state. So that's why I'm using naught, but it cannot be always. It may be delta G also. So most of the question has data of a standard state. That's why I'm using. So delta G naught is equal to delta H naught minus T delta S naught. We can draw the graph of delta G naught versus temperature. And from this graph, we can find out when we are discussing this variation, it should be common sense that in this temperature range, whatever we are changing the temperature, in the particular temperature range, the value of delta H naught and delta S naught is constant. It is not going to vary. So this is constant and this is constant. Here, if you compare, delta H naught is related to the intercept. This is the intercept on y-axis. And the slope, you can see that the slope is equal to minus times of delta S naught. So slope of this line is constant, means delta S naught is constant. Intercept is fixed, means delta H naught is fixed. So if you are drawing a straight line, this is experimental graph, means in that temperature range, the value of delta H naught and delta S naught is constant. So one question is that they will draw the graph of delta G naught versus temperature, and they can ask that reaction is endothermic or exothermic. Like here we are saying that delta H naught is negative, exothermic reaction. Entropy change, because the slope is positive, so entropy change is negative, right? So you can solve questions based on the graph. Now let us discuss an example based on this formula. And this example, I think this example already, these type of examples already asked in JEE mains. So I have seen 2-3 questions based on the same concept. Data may be different also, right? So here, this is a reaction. For the reaction at 300 Kelvin, A in gaseous state plus B in gaseous state will form C in gaseous state. Change in internal energy of this reaction is given. Entropy change is given, and they are asking what is the value of delta G naught, delta G of the reaction. So the first thing is we have to use the relation between delta H and delta U or delta E for a chemical reaction. So using that relation, I can calculate what is the value of delta H. So since here pressure, volume, energy, nothing is mentioned about that, temperature is mentioned. So it is an indication that I have to assume that these gases are ideal, and then this I can apply this formula. So from here, I can write that change in internal energy is equal to minus 3 kilocalorie. So I'm writing in calorie, minus 3000 calorie. The value of delta Ng according to valence reaction, right hand side 1 gas molecule, left hand side 2 gas molecules. So delta Ng will be minus 1. So we'll put here delta Ng is equal to minus 1. Delta Ng is minus 1. The value of R in calorie will be 2. Temperature here is 300. So if we simplify, this value is equal to 3600 calorie. This is the value of delta H. Now we can apply the formula delta G is equal to delta H minus T delta S. So delta H value we already know, 3600. Temperature is 300. Entropy change for this reaction they have given, that is minus 10 calorie per Kelvin. So if we simplify, this value is coming 600 calorie, right? So this answer will match. So these type of questions are very common in JEE mains. So they are simple also. We are studying variation of gas free energy with temperature. This is variation of gas free energy with pressure and temperature for a pure substance. This is for pure substance. Variation of gas free energy with temperature and pressure. So in this, for a pure substance, like we can discuss that what is the variation of gas free energy for an ideal gas. So we are discussing here variation of G with pressure for an ideal gas, So since temperature is constant, so this term is equal to 0. When the temperature is constant, we can say this is 0. So we can write dz is equal to vdp. Since gas is ideal, volume is nRT upon P into dP. If we integrate, we can write delta G is equal to nRT ln P2 upon P1. Since isothermal process is there, temperature is constant, so we can write that P1 V1 is equal to P2 V2. So from there, we can write that what is the value of P2 upon P1. So P2 upon P1 is equal to V1 upon V2. So if I simplify, I will get this value minus nRT ln V2 upon V1, which is equal to the work done in isothermal reversible expansion for an ideal gas. So change in Gibbs free energy for an ideal gas participating in isothermal process is equal to the work done by the gas in a reversible isothermal process. So this is the conclusion we got. Now, what is the difference between Gibbs free energy and work done? Because here the change in Gibbs free energy is equal to work done, but we know that work done is a path variable while Gibbs free energy is a state variable. So try to understand what is the difference between Gibbs free energy and work. So we have taken ideal gas, and this ideal gas is in the first graph, the ideal gas is participating in isothermal reversible process. So here the process is isothermal in both cases, And we know that for isothermal process, if we are changing the volume by the same amount, right? VA to VB, right? So the pressure change, either it is reversible or irreversible, will be same. PA to PB. Here also, if I am changing the volume by same amount, then the pressure change will be same. So pressure at point A and B in both the graphs will be same. Or I indirectly want to say that PA VA is equal to PB VB is valid for isothermal reversible as well as irreversible. It is valid for both. Like in adiabatic, PV to the power gamma is only valid for adiabatic reversible. It is not valid for irreversible, but PAVA is equal to PVVB is valid for isothermal reversible as well as irreversible. So for this isothermal reversible, I know that the change in Gibbs free energy in A to B process is equal to work done in this process. We have proved that. So the work done is equal to change in Gibbs free energy. But suppose this is irreversible process, we don't have graph, right? But since Gibbs free energy is a state variable, if initial and final state is same, the change in Gibbs free energy will be same. So change in Gibbs free energy of this irreversible process is equal to work done in irreversible process, while the work done in this irreversible process is area under this graph, right? So we can say that the change in Gibbs free energy in process A to B is not equal to work done in this process, right? When the process is reversible for isothermal process by an ideal gas, delta G is equal to work reversible, but delta G is not equal to work irreversible. So work is path variable, Gibbs free energy is state variable. Few questions, very simple questions are there regarding Gibbs free energy, and these are very common in exam. Let me read the first question. What is the free energy change delta G when 1 mole of water at 100 degrees Celsius and 1 atm pressure is converted into steam at 100 degrees Celsius and 1 atm? So they are discussing about boiling of water, and boiling is taking place at boiling point. Means there is an equilibrium between liquid and vapor state. When pressure is equal to 1 atm and temperature is 100 degrees Celsius, pressure is 1 atm, then there is an equilibrium between liquid and vapor state. If there is an equilibrium between liquid and vapor state, delta G is equal to 0. So this is a very common simple question. Delta G will be 0. Let us discuss the second example. It is of the similar type but little bit different. What is the free energy change when 1 mole of water at 100 degrees Celsius and 1 atm pressure is converted into steam at 100 degrees Celsius and 2 atm pressure? So here the initial state, water is in liquid state, pressure is 1 atm, 100 degrees Celsius, and finally water is in gaseous, but pressure is not 1 atm, it is 2 atm and 100 degrees Celsius. We have to calculate Gibbs free energy. So all state variable, this point is very important, that whenever we are saying that some variable is a state variable, either I will move from initial state to final state by one path or more than one path. Since initial and final state is same, the change in that variable, state variable, will be same. So what we are doing, that we are converting this H2O to gas at 1 atm and 100 degrees Celsius. So we already know under this condition equilibrium is there, so delta G for this path is equal to 0, and then we'll move from here to here. So this is for gas, temperature is constant and pressure is increasing. So I can say that this is isothermal compression, or we are assuming that the gas is ideal in order to solve it. So isothermal compression. So in case of isothermal compression, change in Gibbs free energy is equal to minus nRT. So the number of moles of gas is equal to 1. Answer is given in calories, so R is 2. nRT, temperature is 100 degrees Celsius, so I can write that is equal to 373.15 Kelvin. So minus nRT ln P1 upon P2. So P1 is 1 atm and P2 is 2 atm. So you can simplify this. So on simplification, you will get the answer, right? So now you have to do the calculation. So if I calculate it, this is 0.36, 546.3, and this ln 2 value, this will be positive. Ln 2 value is approximately 0.7, right? So by multiplying this, we'll get the value. So multiply it and you will get the value. Let me multiply this also. 7 3 times will be 21, and 7 6 42 plus 2 44, then 28 plus 4 32, 35 and 3 38. Here it will be not 5, it is 7, huh? This will be 7, so 746, right? So 7 times 49 and 3 51, right? So this is approximate value 512.49. so it's matching with 512 point. So the nearest possible is D option, right? So D will be the answer. Check it, please check the calculation. I think D will come. So many questions they have asked in the relation between delta G is equal to delta H minus T delta S. In this relation, we can, using this relation, we can predict the spontaneity of a process. So we can divide the reactions, all reactions, in 4 categories. So the first category, in which delta H is negative, this delta H is negative and delta S is positive. We have an example over here. Decomposition of N2O. It is an exothermic process, because when you study formation of N2O is an endothermic process. When nitrogen react with oxygen to form any oxide, it is always endothermic. So reverse of that is exothermic. So this is exothermic reaction. And on the right hand side, there are 3 gas molecules. On the left hand side, only 2 is there. So delta Ng is positive. So delta S is positive. So if I put in this equation, delta G is equal to delta H minus T delta S. Delta H is negative only and delta S is positive, means this delta G is always negative. So that's why this reaction is always spontaneous at all temperature. Similarly, similar to that, there is another reaction. Decomposition of ozone is also spontaneous at all temperature, 3 times of O2, because again here decomposition of ozone is an exothermic process. Delta H is negative. And entropy change, because gas molecules, number of moles of the gas on the right hand side is greater than left. So delta S is positive. So again, delta H negative, delta S positive. Decomposition of ozone is spontaneous at all temperature. That's why we don't prepare ozone and keep for a long time. Whenever we have to use, we have to prepare just before that or sometime before it, because if we prepare it, then it will decompose, and decomposition is spontaneous at all temperatures. So first thing is done. The second example is delta H exothermic reaction. Delta H is negative and delta S is also negative. When delta S is negative, means T delta S will be positive. So one term is negative, other term is positive. So the temperature will decide that at what condition this reaction will be spontaneous. So when the temperature will be low, at low temperature, T delta S value will be small. So at low temperature, when the value of T delta S will be small, we can say that delta H negative part is dominating. So delta G will be negative. So we are saying that at low temperature, this reaction is spontaneous. When temperature is high, the value of T delta S will be more. And we can say that minus T delta S will be more positive than delta H, right? So the net value will be positive. So, and in that condition, we can say that the reaction is non-spontaneous at high temperature. So example is very simple. We are discussing about freezing of water. So freezing of water is spontaneous at low temperature, but freezing of water is non-spontaneous at higher temperature. So very simple example. You can make many examples based on these concepts. The third example is when the enthalpy change of the process will be positive. Enthalpy change is positive and entropy change is also positive. So if entropy change is also positive, means T delta S, this value will be negative, and delta H is positive. So they are opposite to each other. So the sign will be positive or negative. It will depend on temperature. So if the temperature is low, then at low temperature, delta H will dominate with respect to minus T delta S. That's why at low temperature, this reaction is non-spontaneous. At higher temperature, T delta S will dominate over delta H, and that's why the reaction will be spontaneous at higher temperature. So example here, decomposition of ammonia, it is an endothermic process. Delta H for this process will be positive. Delta S for this process will be positive because the number of moles of gas on the right hand side is greater than the number of moles of gas on the left hand side. And temperature will decide that under what condition this reaction will be spontaneous. So we have discussed these three cases. The last case is fourth case, where delta H is positive and delta S is negative. Delta H positive and delta S negative means T delta minus T delta S is also positive. So this delta G is always positive. Reaction is non-spontaneous at all temperature. So this is the example. Formation of ozone. Here we can say that in formation of ozone, this is endothermic process because when from sun radiations are coming, and during ozone formation, that ozone layer absorb ultraviolet light, right? So there is absorption of energy. So that is an endothermic process. So delta H is positive and entropy change is always positive. So it is a non-spontaneous reaction at all temperature. Formation of ozone is a non-spontaneous reaction. Here in this graph, they have explained that if this is the value of delta H reaction, then the value of delta, the sign of delta G will depend on the value of T delta S. So if we are saying that this is the value of delta H reaction, if I'm saying that T delta S reaction with respect to delta H, we are looking here that because delta G is equal to delta H minus T delta S, right? So here they have given that at this point delta G is equal to 0 means delta H is equal to T delta S, right? Delta H and T delta S both. So while considering this, we are assuming that this T delta S value, here T delta S value is positive, here T delta S value is negative. So if T delta S value is negative, and we are writing that delta G is equal to delta H minus T delta S. Delta H minus T delta S. So T delta S, if this whole value is negative, if this is negative and there is a negative sign over here, so this negative and negative will become positive. So if this positive, this whole positive thing is greater than delta H, which is on the left hand side here, if this is greater than delta H, it means that delta G is always positive. Here we are getting that delta G negative because in this region, if you see, this is T delta S, right? And the value of T delta S is positive. T delta S is positive. So when we are writing that delta H minus T delta S, if the value of T delta S is positive and it is greater than delta H, definitely this whole value will be negative. So this is representing a spontaneous part. This is representing non-spontaneous part. So this type of graph they can ask. So try to understand that here T delta S is negative, here T delta S is positive. Another example, Select correct statements for the reaction. The reaction is given. They have given the value of delta H naught formation and entropy of all the reactant and all the product. So they are discussing something about the reaction. So first, if we have heat of formation of all the reactant and all the product, we can apply the formula summation heat of formation of product minus summation heat of formation of reactant. So for this reaction, if we apply the formula, we are getting heat of this reaction is negative. It is an exothermic process. This is an exothermic process. And entropy change of this reaction, entropy of product minus entropy of reactant. So again, from there we are getting that entropy change is negative. So this is an exothermic process. Temperature will decide, because we are saying that delta H is negative, minus 15 kilocalories, so minus 15,000 minus temperature, and this minus minus will become plus into 5. Temperature will decide that when the reaction is spontaneous and when the reaction is non-spontaneous. At low temperature, this value will be negative, so reaction will be spontaneous. At high temperature, it will be non-spontaneous. So if the question, like first they are asking that reaction is enthalpy driven or entropy driven, so you should know that an exothermic reaction is enthalpy driven process. Exothermic, because this is exothermic, because of delta H, this reaction will spontaneous, not because of entropy change, right? Entropy change may be positive, may be negative, right? When entropy change is also negative, then it is spontaneous at all temperature. But when entropy change is like here, entropy change is positive, then it is spontaneous at all temperature. But entropy change is negative, then this term will be positive. So temperature will decide. So it is exothermic reactions are enthalpy driven process and endothermic reactions are entropy driven process. We try to discuss this portion, these two portions they are asking, right? This is regarding enthalpy driven and this is regarding entropy driven, because entropy is deciding that this reaction will happen or not, right? So this is exothermic reactions are enthalpy driven and endothermic reactions are entropy driven. So here we can say that the reaction is exothermic, so it is the reaction is enthalpy driven, that is correct. Reaction is not entropy driven. If it is endothermic, then we can say that reaction is spontaneous at 400 Kelvin. If you want to check that, we can put this formula. Delta G naught is delta H naught minus T delta S naught. Putting the value of delta H naught and T delta S naught, we are getting negative value. So we can say that this reaction is spontaneous at 400 Kelvin. So this is correct. Now, if they are asking in this question that up to what temperature the reaction is spontaneous. So for spontaneity, we can say that delta H naught minus T delta S naught should be negative, and from there we'll calculate at what temperature it should be negative, right? Till what temperature it should be spontaneous. So by solving that, we'll get that till 3000 Kelvin, this reaction will be spontaneous. Till 3000, it will be spontaneous. After 3000, it will non-spontaneous, right? In 2006 JEE Mains, they have asked a question about spontaneity of a process. And this is very important because based on that, we can frame many questions. So it is important for JEE Mains and advanced also. This concept, this question is based on application of Clausius inequality. So we are not going to derive Clausius inequality here, but we know that according to Clausius inequality, change in entropy should greater than equal to dq upon T, or temperature in Kelvin is always positive. So I can bring this on left hand side. We can write that TdS is always greater than dq. Equality is for reversibility and inequality is for irreversibility. So since we are discussing about spontaneity, spontaneous process are irreversible process. So here we are discussing that for spontaneous or irreversible process, TdS should be greater than dq. Now, this process is irreversible. I am using first law of thermodynamics. According to first law of thermodynamics, du is equal to dq minus times of P external into dV. So by using first law, if I put the value of dq in this equation, I can write dq is this value. So from here I can make this conclusion that this is for system, that if the internal energy of the system is constant, means du is equal to 0. If the volume of the system is constant, right, dV is equal to 0, then at constant internal energy and constant volume, the entropy change of the system should be positive for a spontaneous process. This option was given in JEE Mains 2006. Two options are there. So one of them is this option, right? Like in A, B, C, D options, there are two parts. So this is one part, other part is regarding Gibbs free energy. So already in 2006, they have asked this question. Again, we can frame many questions based on that. Again, I am writing that T delta S is greater than dQ and dQ is equal to du plus P external into dV. Now, if the volume is constant and entropy is constant, if entropy and volume is constant, ds is equal to 0 and dv is equal to 0. So these two terms will be 0. Means change in internal energy at constant entropy and volume should be negative for a spontaneous process. So it's very simple. If you know Clausius inequality, you can find out all these conditions. The third condition is, again, we are writing from first law, in place of dq du plus p external into dv. When the pressure and temperature is constant, when pressure is constant, pressure of the system and external pressure will be same. So here du is equal to p external into dv. In that, in place of p external, I can write pressure of the system, and I know that du is p dv. When pressure is constant, this is dh. H is equal to u plus pv. Du plus p dv when pressure is constant is equal to dh. So we can write that dh, this value is equal to dh. So in this equation, I am putting the value. This is TDS. So DH minus TDS. If I put this, because this is DH, so DH minus TDS, this will come, should be less than 0. And from here, we can write that H is G is equal to H minus TS. So when temperature is constant, I can write that dZ is equal to DH minus TDS. So this value is equal to change in Gibbs free energy at constant temperature and pressure. Most of the students remember this. Everybody know about this, right? But this already asked in JEE mains in 2006. So be careful about that. Same way you can derive this fourth relation. It is also a very simple relation. Let us see. TDS is greater than equal to du plus, in place of dq, I am writing by using first law of thermodynamics. If the pressure and entropy is constant, entropy is constant, ds is 0. Pressure is constant means this will be pdv. So this du plus pdv is dh. So dh, right? So if entropy is constant, I can write that change in enthalpy at constant pressure and enthalpy should be 0 for a spontaneous process. So for spontaneity, there are few points. Like according to second law of thermodynamics, the entropy of universe will increase in a spontaneous process. According to system, there are 3-4 things we have studied. One, we remember that change in Gibbs free energy at constant temperature and pressure should be negative for a spontaneous process. Similarly, we can say that change in internal energy at constant entropy and volume should be negative for a spontaneous process, or change in enthalpy at constant pressure and entropy should be less than 0 for a spontaneous process. Or we can say that change in entropy at constant internal energy and volume should be positive for a spontaneous process, right? So this is very important. In few years, like past, I think 2 or 3 years back, there was a question on phase transition. That question was already in NCERT, old NCERT. और ये क्वेश्चन पहले ही नीट में 10 years बिफोर उन्होंने पूछा है. ये क्वेश्चन ऑलरेडी 10 साल पहले पूछा गया है, और दिस वाज देयर इन ओल्ड एनसीईआरटी. So let us discuss this concept, already asked in JEE Advanced. So chances that they can ask in JEE Mains also. So what we are discussing here in phase transition, we are discussing conversion or transition of graphite into diamond. When we are discussing this, the temperature is constant. If the temperature is constant, we know that change in Gibbs free energy dG is equal to VdP minus SdT. When temperature is constant, this will be 0. So dG is equal to VdP. This is for a pure substance. Now we are not discussing pure substance. We are discussing about a process. So d of delta G of the process is equal to delta V of the process into dP. So this is the meaning of this equation. Now here, since graphite and diamond, if we change the pressure, the change in density of graphite and diamond, there is negligible change in density. So we are assuming that when we are changing the pressure, there is no change in delta V of the process. So we are taking delta V outside the integration, and we are moving from initial pressure 1 bar. At when pressure is 1 bar, there is a standard condition. So delta G of this process is delta G naught. And we want to know when this process will be spontaneous. So we are finding first limiting condition. When equilibrium will be 0, right? Means we'll find the pressure when there is an equilibrium between graphite and diamond. Then if we increase the pressure by small quantity, then this process will become spontaneous. So limiting condition we are putting delta G when graphite and diamond at equilibrium will be 0. Delta G will be 0. So if I simplify left hand side, this integration differentiation will cancel out. We can write Gibbs free energy of this process final up minus Gibbs free energy of this process initial. So 0 minus delta G naught of this process is equal to delta V of the process. Final pressure is P bar minus initial pressure. Pressure is in bar, and we know that 1 bar is 10 to the power 5 Pascal. So we are writing the pressure in Pascal. So P minus 1 into 10 to the power 5. Here the volume change, because this we want to write in Joule. So volume change should be in meter cube. What is the volume change of the process when graphite is converted into diamond? Volume change is equal to final volume minus initial volume. We are discussing for conversion of 1 mole of graphite into diamond. So when 1 mole of graphite mass is 12 gram, 12 divided by density of diamond minus 12 divided by density of graphite. So with the help of that, we'll find out that density should be given in gram per centimeter cube. From there, we can find out what is the change in volume. And once we know the change in volume, from there, delta G naught of this reaction is important. Delta G naught of the reaction is equal to delta G naught formation of diamond minus delta G naught formation of graphite. Delta G naught formation of graphite is equal to 0. So we can say that delta G naught of reaction is delta G naught formation of diamond. So in the question, delta G naught formation of diamond should be given. And with the help of that, we can calculate what is delta G naught of the reaction. Once we get the delta G naught of the reaction, we can put in this equation. And from there, we can calculate the pressure. So pressure is very high for this process. So this is a question asked in JEE Advanced, and many years ago it is also asked in JEE NEET exam, and this was given in old NCERT. So keeping all those things in mind, you can solve this question. Now we are coming for thermochemistry. So one thing is important in thermochemistry. When you are solving the question of thermochemistry, two things are required. One is you should know the definition. If you know the definition, and definitions are very logical, right? We'll go one by one, we revise it. If you know the definitions, and definitions are very logical to remember, and if you don't do hurry in plus and minus, you can solve a question of thermochemistry. So let us start, because we know that in thermochemistry we study about different type of heat of reaction, and heat of reaction at constant pressure is known as enthalpy change of the reaction. Under standard condition, it is known as standard enthalpy of formation. So when we are discussing about standard enthalpy of formation, let me read the definition and then we'll write the reaction. So its enthalpy change under standard state when 1 mole of a substance, either it is element or compound, is formed from its constituent elements in their most stable state of aggregation. So here 1 mole will form, and formation can be of element and compound, and it is formed from its constituent elements in most stable state of aggregation. Let me try to explain with the help of example. Suppose if I am saying that I have to form water. So water is a compound and nothing is mentioned. I have to form water at room temperature. At room temperature, water is in liquid state. So this is fixed. If I am saying heat of formation, I have to form 1 mole of water. I have to form 1 mole of water. Constituent elements are 2, hydrogen and oxygen. In nature, hydrogen exists in diatomic form, hydrogen in gaseous state, H2 molecule in gaseous, and oxygen also exists in O2 molecule in gaseous. I can't change the coefficient on the right hand side. So in order to balance, I have to write here half. So this reaction is heat of formation. So what we have to remember, we have to form 1 mole of the substance from its constituent elements, and constituent elements must present in most stable state of aggregation. Suppose I want to form here diamond, artificial diamond. So I will write carbon, solid, diamond. This is element. I have to form this. So in order to form this diamond, I will take carbon, and that carbon is graphite from nature, and I will make it. Right. So this is formation of diamond, artificial diamonds. If I am saying that I have to make nascent oxygen in gaseous state, I will keep the number of moles of this one. I will take nature, from nature oxygen. Oxygen is existing in O2 in gaseous state. I cannot change the right hand side. It is 1. So here I have to multiply by half. So this is formation of nascent oxygen. This is formation of diamond. This is formation of water, right? So heat of formation 1 mole. One is common, 1 mole is common in all these definitions, right? So when something is formed, it may be endothermic or exothermic. Heat of formation may be endothermic or exothermic. Here there are certain examples where we should know that their heat of formation, these are elements, and we know that some of them are most stable state. For most stable state of aggregation for an element not an compound, standard heat of formation is assumed to be zero. Like for graphite, standard heat of formation is zero. Diamond, it is not most stable state of aggregation, non-zero. Phosphorus exists in 3 forms, but for white phosphorus is this assume delta H naught formation is equal to 0, right? For red phosphorus and black phosphorus, it is non-zero. Sulfur exists in 2 forms. You should remember that for orthorhombic, delta H naught formation is assumed to be 0. Monoclinic, it is not equal to 0. Oxygen exists in the form of O2, O3, nascent oxygen. For O2, it is 0. For ozone, it is non-zero. For nascent oxygen, it is non-zero. Hydrogen in nature exists in the form of hydrogen molecule. For that, it is 0. Same with hydrogen and deuterium. Deuterium also will exist in the form of diatomic molecule, right? It is the most stable state of deuterium, not deuterium atom, right? So this delta D2 gas, that is equal to 0. Halogens at room temperature, fluorine and chlorine are gas. So for them, delta H naught formation is equal to 0. At room temperature, bromine is liquid. So for bromine liquid, not gas. ये JEE advance में पूछा गया था. Here they have mentioned gas, and they are asking that key for which it is 0, right? So for liquid at room temperature, it will be 0. For iodine, it is solid at room temperature. So I2 solid, it is 0. Not when I2 is in gaseous state. These are also given in NCERT. Tin exists in 2 forms, tin white and tin gray. For tin white, it is equal to 0. Arsenic exists in 2 forms, arsenic white and gray. For gray, it is equal to 0. And H plus ion, these all are pure substances and element, but this is an ion and it is not pure. It is existing in aqueous medium. H plus ion in aqueous medium, delta H naught formation is equal to 0. So you should remember those things regarding standard heat of formation of element in their most stable state of aggregation is assumed to be 0. By using that, we can solve many problems. So there are many questions in which some data is given, and by going through data, we'll see that many heat of formation is given in some question, many heat of combustion is given in some questions, many bond formation and bond dissociations are given. So if so many bond formation and bond dissociations are given, it is an indication that you should apply a formula summation, right? So there are 4 formula regarding summation. 4 formulae हैं. पहला क्वेश्चन जो पूछा जाता है उसमें सारे रिएक्टेंट और सारे प्रोडक्ट के हीट ऑफ फॉर्मेशन गिवन होते हैं. सो फॉर एनी केमिकल रिएक्शन, एनीथिंग, रिएक्शन इज एनीथिंग, इट डजंट मैटर, एनी केमिकल रिएक्शन, इफ we know heat of formation of all the reactants and all the product, we can apply the formula summation heat of formation of product minus reactant with their stoichiometric coefficient. A मतलब stoichiometric coefficient के साथ में लिखना है आपको. So product minus reactant. दूसरी कंडीशन है when heat of bond formation, we are going to discuss what is difference between heat of formation and bond formation. But if heat of bond formation of all the reactants and all the products are given, then we can apply the formula summation heat of bond formation of product minus summation heat of bond formation of reactant with their stoichiometric coefficient. So again here formation word जब भी आएगा product minus reactant लगाना है. तो 2 में प्रोडक्ट माइनस रिएक्टेंट है और बाकी 2 में रिएक्टेंट माइनस प्रोडक्ट है. इफ हीट ऑफ कंबस्शन इज गिवन, सो हीट ऑफ कंबस्शन ऑफ रिएक्टेंट माइनस हीट ऑफ कंबस्शन ऑफ प्रोडक्ट करना है. अगर हीट ऑफ बॉन्ड डिसोसिएशन है तो रिएक्टेंट माइनस प्रोडक्ट. सो वेरी सिंपल है. इन ऑर्डर टू रिमेंबर 4 फॉर्मूले हैं. 2 में जहां भी फॉर्मेशन वर्ड आ रहा है उसमें प्रोडक्ट माइनस रिएक्टेंट करना है और बाकी 2 में रिएक्टेंट माइनस प्रोडक्ट करना है. In combustion and bond dissociation, it is reactant minus product. So very easy to remember these, right? So these all are 4 formulas where we have to apply. When we are applying this summation formula, like the first formula is regarding heat of formation. This is valid for all chemical reaction. But the second formula, bond formation will take place when the atoms are in gaseous state. So in bond formation and bond dissociation, all the reactants and all the products should be gaseous state. ये सारे reactant और सारे product gaseous में होंगे तभी ये valid है, second and third. And the fourth is combustion. Combustion is also valid for all reactions provided we know heat of combustion of all the reactants and all the products. ठीक है, तो ये चार फॉर्मूले हैं, जेई मेंस में ऐसे ही क्वेश्चन पूछे जाते हैं, फॉर्मेशन दे देंगे और पूछेंगे व्हाट इज हीट ऑफ रिएक्शन. सो लेट अस डिस्कस द सेकंड डेफिनेशन, दैट इज स्टैंडर्ड एंथैल्पी ऑफ बॉन्ड फॉर्मेशन. सो इट्स वेरी सिंपल. व्हेन वी आर सेइंग दैट 1 मोल ऑफ अ सब्सटेंस इज फॉर्म्ड, राइट, यहां मैं पढ़ देता हूं फिर मैं इसको एक्सप्लेन करता हूं विद द हेल्प ऑफ एन एग्जांपल. Its enthalpy change in standard state when 1 mole of a substance in gaseous state will form from its constituent element in gaseous state and atomic form. It's always exothermic process. So 1 मोल तो है, फिक्स है ना. अब ये सब्सटेंस एलिमेंट भी हो सकता है, कंपाउंड भी हो सकता है. जैसे मैंने अगर कहा कि मुझे बॉन्ड फॉर्मेशन करना है तो सब्सटेंस गैसियस स्टेट में ही होना चाहिए. तो अगर मुझे वाटर का बॉन्ड फॉर्मेशन करना है तो ये वाटर गैसियस स्टेट में होना चाहिए. अब ये 2 एलिमेंट से बना है, इसका 1 मोल ही बनना चाहिए. 2 एलिमेंट है हाइड्रोजन और ऑक्सीजन, बट ये हाइड्रोजन और ऑक्सीजन जो है वो गैसियस स्टेट और एटम के फॉर्म में होने चाहिए. सो हाइड्रोजन एटम एंड ऑक्सीजन एटम इन गैसियस स्टेट. आई कांट चेंज द कोफिशिएंट ऑन द राइट हैंड साइड, सो आई will write here 2 in order to balance it. So this reaction is heat of bond formation of H2O मॉलिक्यूल इन गैसियस स्टेट. अगर कोई एलिमेंट है, जैसे अगर मैं कहता हूं हाइड्रोजन एलिमेंट है, इसके बॉन्ड फॉर्मेशन की बात करनी है, 1 मोल होना चाहिए. किससे बना? हाइड्रोजन एटम से. सो हाइड्रोजन इन गैसियस स्टेट, हाइड्रोजन इन गैसियस स्टेट. विल से दैट दिस रिएक्शन इज रिप्रेजेंटिंग हीट ऑफ बॉन्ड फॉर्मेशन ऑफ हाइड्रोजन मॉलिक्यूल. तो चाहे वो एलिमेंट हो या वो कंपाउंड हो, फॉर्मेशन, बॉन्ड फॉर्मेशन में सारे रिएक्टेंट और सारे प्रोडक्ट गैसियस में होने चाहिए. और आपको ये दिख भी रहा होगा ना कि एटम मॉलिक्यूल बना रहा है मतलब बॉन्ड फॉर्मेशन हो रहा है. तो इसमें रटने वाला कुछ भी नहीं है, राइट. इट्स अ वेरी सिंपल थिंग, लॉजिकल थिंग. थर्ड इज स्टैंडर्ड एंथैल्पी ऑफ बॉन्ड डिसोसिएशन. देयर बॉन्ड डिसोसिएशन इज जस्ट रिवर्स ऑफ बॉन्ड फॉर्मेशन. जैसे अगर मैं कहता हूँ CH4 मॉलिक्यूल गैसियस स्टेट में है, अगर मुझे इसका बॉन्ड तोड़ना है, ये 1 मोल होना चाहिए और इसके सारे बॉन्ड तोड़ के इसको एटॉमिक फॉर्म में लाना है. कार्बन इन गैसियस स्टेट प्लस 4 टाइम्स ऑफ हाइड्रोजन इन गैसियस स्टेट. So 1 mole should be there and all the reactant and all the product should be in gaseous state. It is always an endothermic process. Hydrogen molecule है, bond dissociation की बात हो रही है. So I can write that it will form 2 times of hydrogen atom in gaseous state. Here coefficient should be 1. अगर कई बार यहाँ coefficient 2 है, यहाँ 4 है, तो it is 2 times of bond dissociation, right? This is bond dissociation. कई बार ये पूछा जाता है, मेंस और एडवांस दोनों में पूछा जाता है कि इनमें से कौन सा बॉन्ड डिसोसिएशन, एंड दे विल राइट लाइक दिस एंड दे विल आस्क दैट व्हिच ऑफ द फॉलोइंग रिएक्शन इज बॉन्ड डिसोसिएशन. अगर मैं इस रिएक्शन का डेल्टा एच लिखूं तो दिस इज 2 टाइम्स ऑफ डेल्टा एच बॉन्ड डिसोसिएशन. इट इज नॉट बॉन्ड डिसोसिएशन, इट इज 2 टाइम्स. सो बी केयरफुल अबाउट द डेफिनेशन. व्हेनेवर वी आर डिस्कसिंग फॉर 1 मोल. तो अगर 2 मोल है तो भी वो बॉन्ड डिसोसिएशन नहीं होगा, इट इज 2 टाइम्स ऑफ बॉन्ड डिसोसिएशन, राइट. So this is about bond dissociation. Now the next definition is standard enthalpy of atomization. कई बच्चे जो हैं वो bond dissociation, sublimation और atomization में confuse हो जाते हैं. बहुत simple है, उसको discuss कर लेते हैं. पहले अपन atomization को discuss करते हैं. Its enthalpy change in standard state when 1 mole of a substance, ये substance कुछ भी हो सकता है, solid state, liquid state, element हो सकता है, compound, कोई भी substance हो, is converted into its constituent atoms in gaseous state and atomic form. तो डेफिनेशन में कोई भी सब्सटेंस है उसका 1 मोल होना चाहिए. अब वो सब्सटेंस के जो एलिमेंट है वो गैसियस स्टेट और एटॉमिक फॉर्म में जाने चाहिए. लेट अस डिस्कस दिस. अगर मैं ये कहता हूं कि सोडियम मेटल सॉलिड स्टेट में है और इसका 1 मोल अगर मैं गैसियस स्टेट में भेज दूं, सोडियम एटम से बना हुआ है, इसको गैसियस में भेज दें, तो ये हो गया एटमाइजेशन. मैंने इसको एटमाइज कर दिया. ये सब्सटेंस सॉलिड स्टेट में था, अब मैंने इसको एटॉमिक फॉर्म में भेज दिया, तो ये एटमाइजेशन हो गया. ये सब्लिमेशन भी है. तो समटाइम्स एटमाइजेशन जो है वो सब्लिमेशन के बराबर हो जाता है. जैसे अगर मैं ये CH4 मॉलिक्यूल लूं, गैसियस स्टेट में है, अब मुझे इसको एटमाइज करना है, इसको एटम के फॉर्म भेजना है. इसका 1 मोल हो गया, इसके जो भी इसको एटमाइज करना मतलब मुझे सारे बॉन्ड तोड़ने पड़ेंगे. आई हैव टू ब्रेक ऑल दिस बॉन्ड. So here we can say that this is atomization of CH4 as well as bond dissociation भी है. This is bond dissociation of CH4 also. So sometimes, जैसे अगर मैं ये कहता हूं कि H2O लिक्विड स्टेट में है और मुझे इसको एटमाइज करना है, तब मैं लिखूंगा 2 टाइम्स ऑफ H इन गैसियस स्टेट प्लस ऑक्सीजन इन गैसियस स्टेट। अब मैं इसको ये नहीं कह सकता कि ये बॉन्ड डिसोसिएशन है। समटाइम्स atomization is equal to bond dissociation, sometimes atomization is equal to sublimation, and sometimes it is not equal to these. अगर मुझे इसमें समझाना है तो ये मैं कहूंगा कि this is delta H atomization, मुझे 1 मोल एटमाइज करना था ये H2O को, तो मैंने गैसियस स्टेट में भेज दिया. आई कैन से इट इज सम ऑफ टू प्रोसेसेस. आई कैन से दैट first I will vaporize this H2O into gaseous state and then I will convert into this atom, right? So this is delta H vaporization and this is delta H bond dissociation, right? Or atomization of H2O gas. So it's very simple. Whatever the substance it is, 1 mole तो हर definition में लेना है, and then you have to convert into atomic form in gaseous state. तो atomization हो गया. गैसियस स्टेट में ही तो एटॉमिक फॉर्म में होंगे ना, एटम्स अलग अलग होंगे, तो नाम भी बहुत लॉजिकल है, राइट? So I don't think that you will forget about this atomization. Now, I was going through the past year questions, and in JEE Advanced also, this is fixed. This relation is fixed. There are many questions based on this relation. By reading the question, you should realize that they are asking this relation. जैसे अभी मैं एक रिलेशन लिख रहा हूँ, हीट ऑफ फॉर्मेशन, हीट ऑफ बॉन्ड फॉर्मेशन, हीट ऑफ एटमाइजेशन में जो तीनों डेफिनेशन हमने पढ़ी है उसका एप्लीकेशन है. एंड ये वाला क्वेश्चन जो है वो जेईई मेंस में पूछा गया है. एंड दिस इज वेरी कॉमन. CH4 मॉलिक्यूल इन गैसियस स्टेट है. अगर मुझे इसका फॉर्मेशन लिखना है तो अब मुझे पता है कि फॉर्मेशन की डेफिनेशन कार्बन सॉलिड ग्रेफाइट होना चाहिए, इसका 1 मोल बनना चाहिए, कार्बन और हाइड्रोजन से बना, नेचर में हाइड्रोजन मॉलिक्यूल के फॉर्म में एग्जिस्ट करता है. अब मैं इसको अगर सब्लिमेट कर दूं, मैं अब इसको क्या है कि ये हो गया फॉर्मेशन. अब मैं बॉन्ड फॉर्म करना चाहता हूं. बॉन्ड फॉर्मेशन में क्या होगा, कार्बन गैसियस स्टेट में होगा और ये जो हाइड्रोजन है वो एटॉमिक फॉर्म में होगा. सो दिस इज डेल्टा, ये जो प्रोसेस है ये हो गया डेल्टा H बॉन्ड फॉर्मेशन, और ये जो प्रोसेस है वो हीट ऑफ फॉर्मेशन ऑफ CH4 है. अब ये इनिशियल स्टेट है, दिस इज इनिशियल स्टेट and this is final state. In order to move from initial state to final state, either I will follow this path or I will first move from here to here and then I will move from here to there, right? So ये जो वैल्यू होगी इसको मैं कह सकता हूँ एटमाइजेशन ऑफ ग्रेफाइट, और मैं कह सकता हूँ सब्लिमेशन ऑफ ग्रेफाइट, दोनों ही सही हैं. ये क्या हो गया, इसका कोफिशिएंट, इस मॉलिक्यूल को तोड़ रहे हैं तो मैं इसको कह सकता हूँ इट इज 2 टाइम्स ऑफ बॉन्ड डिसोसिएशन ऑफ हाइड्रोजन मॉलिक्यूल. मैं ये भी कह सकता हूं कि इट इज 2 टाइम्स ऑफ फॉर्मेशन ऑफ हाइड्रोजन एटम. अब ये सारे रिलेशंस अगर मैं लिखता हूं, पहला रास्ता हो गया हीट ऑफ फॉर्मेशन ऑफ CH4, दूसरा रास्ता हो गया हीट ऑफ सब्लिमेशन ऑफ ग्रेफाइट प्लस डेल्टा H बॉन्ड डिसोसिएशन ऑफ हाइड्रोजन मॉलिक्यूल और डेल्टा H बॉन्ड फॉर्मेशन. सो इन द क्वेश्चन डायरेक्टली क्वेश्चन ही बोलेगा आपको कि ये रिलेशन लिखना है, ठीक है. कई लोग जो है उसको थर्मोडायनेमिक ऑपरेशन से सॉल्व करते हैं, बट इफ यू गो थ्रू द डेटा वेरी लॉजिकल, यू विल नॉट डू एरर if you are trying to write in this way, right? Based on that, there is some questions will practice, will not solve the question completely, time is limited. मैं केवल रास्ता बताऊंगा कैसे सॉल्व करना है. जैसे अभी ये क्वेश्चन है, इसमें कार्बन सॉलिड हाइड्रोजन और ये जो भी कंपाउंड बन रहा है, आइसोप्रीन नाम लिखा हुआ है, दिस इज आइसोप्रीन, वी हैव टू फॉर्म दिस कंपाउंड, आइसोप्रीन है. अब इसमें देखो ये 1 मोल बन रहा है और इसमें कार्बन और हाइड्रोजन है, या कार्बन सॉलिड लिखा है, अंडरस्टूड है, डायमंड से तो बनाएंगे नहीं, ये ग्रेफाइट ही है, और ये हाइड्रोजन मॉलिक्यूल इन गैसियस स्टेट है. सो दिस इज फॉर्मेशन रिएक्शन. ये जो रिएक्शन लिखी है ना, ये हीट ऑफ फॉर्मेशन ऑफ आइसोप्रीन है, बिकॉज elements are present in most stable state of aggregation on the left hand side. यहाँ राइट में 1 मोल है. So this is delta H formation of isoprene. और यहाँ बॉन्ड डिसोसिएशन ऑफ कार्बन हाइड्रोजन बॉन्ड है, कार्बन कार्बन है, हाइड्रोजन हाइड्रोजन है, कार्बन डबल बॉन्ड कार्बन है. तो अगर मैं इस पूरे मॉलिक्यूल के लिए बॉन्ड डिसोसिएशन लिखता हूँ कि व्हाट इज बॉन्ड डिसोसिएशन, तो इसमें कार्बन डबल बॉन्ड कार्बन 2 हैं, तो आई विल राइट 2 टाइम्स ऑफ कार्बन डबल बॉन्ड कार्बन. इसमें कार्बन कार्बन सिंगल बॉन्ड एक ही है, नहीं 2 है, तो आई विल राइट 2 टाइम्स ऑफ कार्बन कार्बन सिंगल बॉन्ड. कार्बन हाइड्रोजन बॉन्ड, जितने हाइड्रोजन एटम होंगे उनको गिन लेते हैं, 2 2 4 8. So I can say that this is 8 times of carbon hydrogen bonds are there. So अगर मैं इन सबको ऐड करूंगा तो I will get the bond dissociation of this whole molecule. If I know bond dissociation, I know bond formation. And this is sublimation. तो क्या क्या इंफॉर्मेशन है, फॉर्मेशन के बारे में पूछा जा रहा है. This is formation. They are asking about formation. They have given about bond formation or bond dissociation. They have given about sublimation of graphite. They have given about sublimation of graphite. So indirectly they are saying that write the relation between heat of formation and bond formation. What we have to do, that we have to write 5 times of carbon in solid state plus 4 times of hydrogen in gaseous state will form this isoprene. So I'm not writing the formula, I'm writing here gas. Now what we have to do, we have to sublimate 5 times of carbon in gaseous state. बॉन्ड सारे ब्रेक कर दो, 4 मॉलिक्यूल्स हैं, 4 टाइम्स ऑफ बॉन्ड एसोसिएशन, सो 8 हाइड्रोजन एटम्स इन गैसियस स्टेट, और ये सब कंबाइन होंगे तो ये बनेगा आइसोप्रीन. तो दे आर आस्किंग अबाउट दिस. They have given 5 times of sublimation. Sublimation energy is 171. Bond dissociation of hydrogen, hydrogen single bond 4 times of 104. और ये अभी हमने कैलकुलेट किया, इससे हम कैलकुलेट कर लेंगे. This is bond formation. Bond dissociation we know, so we know bond formation. So with the help of this, I can calculate what is the value of formation of isoprene. So many questions based on the same concept, relation, right? So you should know this relation. It's easy, logical to solve the question. Here also one question is based on the same concept. Using the data, calculate the enthalpy of formation of acetone. Acetone की formation के लिए, तो we know that if we want to write formation of acetone, CH3COCH3 should be in gaseous state. Question में दे रखा गैस है ना, और ये कार्बन और ऑक्सीजन और हाइड्रोजन से बना है. कार्बन सॉलिड, ये अंडरस्टूड है कि ग्राफाइट की बात कर रहे हैं. कार्बन के 3 एटम्स हैं. देन हाइड्रोजन 6 हैं, 3 टाइम्स ऑफ हाइड्रोजन मॉलिक्यूल इन गैसियस स्टेट. ऑक्सीजन का 1 मॉलिक्यूल है, हाफ टाइम्स ऑफ ऑक्सीजन इन गैसियस स्टेट, 1 एटम है. सो दिस इज द बैलेंस रिएक्शन. 1 मोल बनाना है, ये हो गया. अगेन यू कैन सी द डेटा हियर. बॉन्ड डिसोसिएशन एनर्जी दे रखी है इन सब की, सब्लिमेशन ग्रेफाइट की दे रखी है, बॉन्ड एनर्जी ऑफ हाइड्रोजन और ऑक्सीजन, ये सब कह रहे हैं कि राइट दिस रिलेशन. 3 टाइम्स ऑफ कार्बन इन गैसियस स्टेट, 6 times of hydrogen atom in gaseous state plus oxygen atom in gaseous state, they will combine to form this. So the question will tell that what you have to do, and these things are very common. From data you can find out. Hope you will able to follow this. This is also based on summation, because they are saying enthalpy of atomization. Whenever you have given some information, if you understand what is definition of atomization, to convert into chemical reaction. pH3 in gaseous state atomize, ये गैस ही होता है रूम टेम्परेचर पे, तो इसको एटमाइज करना, we have to write phosphorus gas plus 3 times of hydrogen gas. For this reaction they have given that 954. ये bond dissociation है, we know that this value is equal to 3 times of bond energy of phosphorus hydrogen bond, this that is equal to 954. And the second is P2H4, so we should know the structure of P24. It is like N2H4, ये ऐसा होना चाहिए. P2H4 का स्ट्रक्चर N2H4 की तरह ही होना चाहिए. This is the structure. So again we have to atomize this. If we atomize, there is 2 phosphorus atom and 4 hydrogen atom in gaseous state. So we can say that bond dissociation energy है. So this is bond energy of phosphorus, phosphorus single bond plus 4 times of bond energy of phosphorus hydrogen single bond. This value is equal to 1485. From here we put the value of phosphorus hydrogen single bond, we can find out what is the bond energy of phosphorus phosphorus single bond, right? So in thermochemistry, if you remember the definitions, and if you remember it, if some language is given, convert that language into reaction. If some reaction is given, by looking the reaction you will find out what information they have given, right? So it is based on these things only. Last point I want to discuss here, thermodynamic operation. These things are very common in thermochemistry. Like one reaction, they will ask that what is delta H of this reaction. So I can name that this reaction is reaction number 1. And certain data is given, like here we can say this is reaction number 2, this is reaction number 3, this is reaction number 4, this is reaction number 5. Now let me read the question first. Hydrogen is a component of rocket fuel, undergoes combustion to yield nitrogen and water. The reaction is given here. What is the enthalpy change on combustion of hydrogen? So this is combustion reaction only. 1 mole is reacting. we should check that the reaction is balanced or not. So I think reaction is balanced, hydrogen is balanced, oxygen is balanced, nitrogen, so it is a balanced reaction. So ये combustion reaction है और इस reaction का हमें डेल्टा एच चाहिए, वन reaction का डेल्टा एच कैलकुलेट करना है। और बहुत सारी reactions, 4 reactions दे रखी हैं, इन रिएक्शंस की मदद से हमें इस रिएक्शन के बारे में पता करना है। बहुत सिंपल है। We'll try to write this reaction. पहली रिएक्शन को हमें इन सारी रिएक्शंस के टर्म में लिखना है। अब जैसे पहली रिएक्शन में ऑक्सीजन भी है, लेकिन ऑक्सीजन यहाँ 2 रिएक्शंस में है, तो हम पहले ऑक्सीजन को रिलेट नहीं करेंगे। N2H4 in the first reaction is there on left hand side. N2H4 here is in 2 reactions. We'll avoid to use N2H4 because it is present in 2 reactions. Then N2 nitrogen gas here is present only in 1 reaction. So I can use nitrogen to proceed forward because water is there in many reactions. तो हम नाइट्रोजन से शुरू करते हैं। नाइट्रोजन here is present on the right hand side and we need it on right hand side, but the coefficient of nitrogen here is 1, but we need here it is 4, right? We need 1 here, right? So what we'll do that, 2 को reaction number 2 को as it is लिखते हैं, इसको 1/4 से डिवाइड कर देते हैं। By doing that what we have done, अगर हमने फर्स्ट सेकेंड रिएक्शन को लिया तो इसके साथ वाटर आया, इसके साथ N2 आया, NH3 आया। N2 और NH3 नेट रिएक्शन में नहीं है, मीन्स हमें वी हैव टू रिमूव दिस, राइट? तो हम क्या करेंगे, अब हमने जब 1/4 से मल्टीप्लाई किया तो लेफ्ट हैंड साइड में N2O 3/4 हो गया। N2O और कहाँ है? थर्ड रिएक्शन में। ये लेफ्ट में है, ये भी लेफ्ट में है, तो इसको अगर मैं राइट में ले जाऊंगा तो ये N2O कैंसिल आउट हो जाएगा। सो आई एम डूइंग मैथमेटिक्स, व्हाट आई एम डूइंग दैट, इफ आई मल्टीप्लाई द थर्ड रिएक्शन बाई 3/4 और माइनस साइन लगा दूं, ये तीसरी रिएक्शन को मैंने यूज कर लिया। ऐसा करने से, ठीक है, अगर मैं ऐसा करूंगा, इसको पूरे से माइनस से मल्टीप्लाई कर दूंगा तो प्रोडक्ट रिएक्टेंट में आ जाएंगे, रिएक्टेड प्रोडक्ट में चला जाएगा। सो आई एम यूजिंग दैट, बाय यूजिंग दिस आई हैव कन्वर्टेड दिस रिएक्शन इनटू दिस फॉर्म, जहां से मैंने N2O को गायब कर दिया। N2O इज नाउ नॉट इन द रिएक्शन। नाउ बाय डूइंग दैट, हाइड्रोजन थर्ड रिएक्शन में, ओवरऑल रिएक्शन में हाइड्रोजन है ही नहीं, तो अब मुझे हाइड्रोजन को गायब करना है। जब मैंने इसको 3/4 से मल्टीप्लाई किया और माइनस साइन लगाया, ये हाइड्रोजन मॉलिक्यूल 9/4 और राइट में चला गया, कोफिशिएंट 9/4 है और इट इज प्रेजेंट ऑन द राइट। तो अब मुझे इसको लेफ्ट में रख के कैंसिल आउट करना है क्योंकि आई डू नॉट नीड हाइड्रोजन। सो व्हाट आई विल डू दैट, 9/4 टाइम्स ऑफ रिएक्शन नंबर 5। ऐसा करने से अभी एक रिएक्शन बच गई है, वो है फोर्थ रिएक्शन। और फोर्थ रिएक्शन में हमें देखना है कि हम फोर्थ रिएक्शन को कैसे यूज कर सकते हैं। ओके, तो जब हमने सेकेंड रिएक्शन को यूज किया तो सेकेंड रिएक्शन में अमोनिया भी था, राइट? N2O और अमोनिया, हमने N2O को गायब किया था, अमोनिया भी गायब नहीं हुआ। ओवरऑल रिएक्शन में अमोनिया इज नॉट देयर, वी हैव टू रिमूव दिस अमोनिया। सो व्हेन वी हैव मल्टीप्लाइड द सेकेंड रिएक्शन बाय 1/4, ये हो गया हाफ। तो अब अमोनिया हमें हाफ करके रिमूव करना है, ये लेफ्ट में ही है, अब मुझे इसको राइट में भेजना है। तो व्हाट आई विल डू दैट, आई विल मल्टीप्लाई 1/8 और मुझे राइट में भेजना है, तो इसको मैं माइनस साइन लगा देता हूँ ऑफ रिएक्शन नंबर 4, राइट? तो अभी हमने क्या किया कि फर्स्ट रिएक्शन को फाइंड आउट करने के लिए हमने ये चारों रिएक्शंस यूज करी, एक बार ही हर रिएक्शन यूज होगी। और हमें क्या ध्यान रखना है, जैसे यहाँ इस रिएक्शन में N2H4 2 जगह था, हमने शुरुआत N2H4 से नहीं करी। ऑक्सीजन 2 जगह था, हमने ऑक्सीजन से शुरुआत नहीं करी। वाटर कई जगह था, हमने वाटर से शुरुआत नहीं करी। हमने उस केमिकल स्पीसी को पहले पकड़ा जो केवल एक ही रिएक्शन में है, और फिर वहां से कुछ आया, उसको इंटरकनेक्ट किया, और मैथमेटिकली वी शुड राइट लाइक दिस। सो दिस इज वन ऑफ द डिफिकल्ट क्वेश्चन ऑफ थर्मोकेमिस्ट्री, ये सबसे डिफिकल्ट क्वेश्चन है। तो कुछ लोग क्या करते हैं कि किसी गिवन डेफिनेशन से वो फॉर्मेशन, जैसे ये हीट ऑफ फॉर्मेशन ऑफ वाटर आ गया, फिर वो कोशिश करेंगे कहीं से और किसी की फॉर्मेशन कैलकुलेट करना, बट दिस इज वेरी डिफिकल्ट इफ यू डू लाइक दैट। दिस इज द मोस्ट इजीएस्ट वे। बाय डूइंग दिस there is no confusion, error chances will be less, and you are very good at mathematics, you can do it। ठीक है, तो अभी इस गिवन टाइम में मैं थर्मोकेमिस्ट्री में इतनी ही चीजें डिस्कस कर पाया हूं, और मैंने कोशिश की है आपको कि जो भी थर्मोडायनेमिक्स और थर्मोकेमिस्ट्री में इतने कम समय में जो भी बेस्ट हो सकता है वो हमने किया है। चलिए, It is not possible to cover all the topics of thermochemistry in this given time. So I have discussed the most important points regarding this topic. Hope you like it. अगर आपको ये वीडियो पसंद आ रहा हो तो प्लीज लाइक जरूर करें. थैंक यू.